Let us look together at this question. Please pause the movie and try it by yourself. I'm reading the question and extracting the important information. So y is normally distributed with an unknown mu and the known standard deviation. I write the null and alternative hypothesis. It's a two-tailed test. We take a sample of size 16, therefore the sampling distribution of the means is normal with the same mean and standard deviation sigma over square root of n. I draw a diagram so that I picture for myself, I visualize the question. I am given this time the critical region, which is outside 329 and 331. Please notice that that's a symmetric interval. So we do two-tailed hypothesis testing for distributions that are symmetric. And I'm asked about the significance level. Significance level is a sum of these two probabilities, and because it's symmetric, it's that area times 2, or the other area times 2. So to find the significance level, I'm going to calculate this area, or this, and times it by 2. So under H0, I always assume the actual state to be the correct one, the true one. I find this area. It doesn't matter if it's less or less equal, it's a continuous distribution. I like to write a conditional probability of y bar smaller than 3 to 9, given that y bar is normal. So I want all the time link the variable with the distribution so that you know where you look at. We have many distributions coming together to a question. You can use a calculator here, or you can standardize. Probably you hear the wind outside. It's very windy. Okay, you can do it in one step by using a calculator. And that's my answer for the area to the left. If your sample is in the lowest 0.275%, then it's considered to be an odd one. Same if it's in the upper tail. So the significance level is 4.55%. Okay, so let's look at question B. Now, 4.55 is your answer to question 1. Probability of a type 2 error. So I write the definition. I always write the definition to make it clear to myself what I need to find. When do I accept H0? When I'm in the acceptance region. So between 329 and 331. What does it mean that H0 is false? It means that mu is not 330, and the new mean is given. The mean will be 328. Always this will be given. So that's my new distribution. So I need to calculate this probability on this new distribution. I can again standardize or use a calculator. So then I calculate the probability, which is a probability of a type 2 error. Please pause the movie and read this question. Try it by yourself. When I read the question, I extract the important information. That gives me the null hypothesis. Fair coin probability of getting an head is half. The next bit gives me the alternative hypothesis. So it's a one-tailed test. Let's see what is the distribution of my test statistic. What I'm trying to do is tossing the coin 12 times. X is the number of heads. That's my test statistic. That's how I decide, based on the number of heads, what's the distribution of the test statistic. Binomial, 12 trials, and P is the probability of success. I always work under H0. So under H0, that's my null distribution. I create a diagram to visualize the acceptance and rejection regions. It is a discrete distribution with values from 0, 1 up to 12. I know the shape of the distribution, so I know that the probability first increase then decrease. I have a decision rule for x bigger or including 10. I reject H0 and here I accept H0. So if x is smaller than or equal to 9, I accept H0 and here I reject H0. This region is called critical region and I answer question I. What is meant by a significance level? Make sure that not only you know the definitions by heart, but you understand their significance. So let's look at the second question. Find the value of the significance level for this test. So now I know that it's a probability of x being bigger or equal than 10 on my distribution, on this distribution. I can use directly my calculator, or I can split it up into 3 and add them. So I need these probabilities on this distribution, and that's my answer. Let us now look at the third question. In fact, the coin is biased, and that's a probability of success, so your distribution changes. Probability of a type 2 error, I always start with the definition and said before. It's probability of accepting H0, and that's my accepting region on the condition that H0 is false. So x smaller or equal than 9, but this time x is, when H0 is false, H1 is true, and I need to be given what is that new probability, 0.6. So it's probability of x smaller or equal than 9 on the new distribution, and that's a probability of a type 2 error. Now I'm asked, if error uses a decision rule from B, what type of error is he making? And the key lies in question C. It says, in fact, the coin is biased. So in fact, H0 is false. Therefore, he is at risk at making a probability of a type 2 error, at risk, but not necessarily is making it. So he's making a type 2, he will make a type 2 error in the case when he accepts H0, but H0 is false. Again, please pause the movie, read the question, and try it by yourself. I am again going through the information to extract the important mathematical aspects. This gives me the distribution of the test statistic. The next information gives me the null versus alternative hypothesis. So when I read, I extract the information in a form that will help me focus quicker on it rather than reading through the text. H1, is lambda equals 5, suggesting a right tail test. Lambda is bigger than the lambda from H0. The next information gives me the decision rule. And now I'm drawing a diagram to picture how the distribution is, what are my acceptance and rejection regions. So let us look next at what question asks. For n equals 1, my distribution will be Poisson of lambda. Probability of rejecting H0 given that H0 false. Always talking in terms of H0, H0 true. And we know that's a type 1 error now. So probability of x being bigger or equal than 4 on this distribution under H0. So under H0 lambda is 2. I calculate this probability on a Poisson distribution and that's my answer. That's a probability of a type 1 error. Next question asks me what's the probability of a type 2 error. Accept H0 given that H0 false. I always think in terms of H0. So accept H0 is here on the new distribution. Lambda is 5 and equals 1. And I calculate this probability. Question B, read again the question. Pause the movie and read again the question. That's a bit different from the previous ones. So I'm asked what is n such that probability of a type 2 is smaller than 0.5%. And I'm going to write this mathematically. I use the formula for the Poisson distribution. The probability of x smaller or equal than 3. And now think how you can use your calculator smartly to solve this equation. It can be by trial and improvement. That's what I used. So I have a column for the values of n, and I have a column from the left-hand side of this equation. And I want to see where this one is smaller than 0.005. I insert the formula here, which is the left-hand side. Forgot to start my formula with an equal sign. And now I see that these values are bigger than the right-hand side, and the first one, which is smaller, is n equals 3. So my answer is 3 minutes are required. The last question is in line with what we've done by now. I'm showing you here how I chose this number. This is a very interesting question. Please pause the movie, read it, and try it by yourself first. I decided at that time I'm going to play quickly my writing, and I'm going to talk through at the end. Here is a better representation of H0 versus H1. It's like you are not very sure what you put in your bag. You think that you put 20 white and 80 black, but somebody comes and said, no, we actually put 50 white and 50 black. So you test H0 against H1. The decision rule is given. If you draw without replacement for black, because it makes sense, there are a lot of black here, so if you draw 4 black, you'd assume it's that case. It's very unlikely to draw 4 black in a row from this bag. And you reject, but that's very subjective, that's your decision rule, but we go against it, we go with it. And you reject H0 otherwise. Probability of a type 1, I go with the definition. Probability of at least one not black, it's always easier to do 1 minus probability of all black. Probability of a type 2 error, same. And in question B, I'm asked about the power of the test. So I'm going to talk a bit about the concept of the power of a test, which is not specifically in your syllabus, but it's an important concept and can be asked in various ways without actually naming it power of the test. I will not go back to question C in detail because it's the same as the second part of question A, and that's question B, sorry. Here I added what we already know about type 1 and type 2 error. Now remember, the power of a test is defined at 1 minus probability of a type 2. And because I'm doing a type 2 error, I'm in the condition when I'm under H0 false. So I'm here. Now these two probability add up to 1. Because if H0 is false, I either accept H0 or I reject H0. So therefore, 1 minus probability of a type 2 is this zone. And it's a power of the test. So the power of the test is the probability of rejecting H0 when H0 is false. So I make a correct decision. But with my decision, I change the status quo. I change H0, I change the situation as it is now. So that's why it's very powerful. The bigger that percentage, the better if I'm to change the way I'm doing things now. So see, in this case, the old test has a greater power, because for the new test, the power of the test is 69.1%, for the old test is 94.1%. At the end of the movie, you can stop and reflect a bit. How does it make sense in the context of the situation? Okay, let us look together at this question. I hope you stopped and you thought of it by yourself. So we are told that the magician says that he gets, as an average, 9 times out of 10 a 6. So the actual state is probability of success being 0.9. The alternative hypothesis will be p smaller than 0.9, because we know that the fair dice actually have a probability smaller than 90% to get a 6. We look at the sampling distribution of the test statistic, and is binomial. We've been told that the experiment is rolling 6 times the dice. Under H0, that's a probability of success. calculate the probability that his claim is true. So his claim is 5 or more 6s under this distribution. There are many ways to calculate the probability. You choose a way, including a calculator, or as I did, and that's your answer. In II, he says that he can roll a 6 on average only once in every 6 rolls. So the distribution changes. We just roll the die 6 times, and that's a probability of success we are looking for. And that's the new probability asked on the new distribution. Question B, maybe you noticed, in question BI, you are asked about the type 1 error without being named the type 1, and in II, you are asked about the type 2 error without it being named as being a type 2 error. We will look together at this question too. Please pause the movie and read the question. So we're looking at X following a Poisson distribution with a mean M and testing the null hypothesis M equals 3 against the alternative hypothesis M equals 4. So how do we form our test statistic? How do we test this test statistic? Is that we form a new random variable, let's call it S, which is x1 plus x2 plus xn, x9, with replacement, right? So that how we think about it is that we create 9 clones of the original distribution X. From each of the clone, we take one observation, and then we add those observations. We add what we see. What we see, of course, there will be numbers to be able to add them, but that's less important. So we add what we see. The question is, what will be the sampling distribution of the test statistic? Because I want to see how odd or unusual this test statistic is when I do one observation. So I know that if x1, x2, xn are Poisson, I know that S is Poisson as well, because I know when I add Poisson distribution, the result will be Poisson, and the mean will be 9m. We know this from an earlier chapter. I'm also given the decision rule. So the decision rule is accept H0 if S is smaller or equal than 37. Reject H0 if S is bigger than 37, right? Yes, bigger than 37. So for S, I'm looking again at this distribution, sampling distribution of the test statistic. A, find the significance level of this test. Significance level is a probability of a type 1 error. So it's probability of rejecting H0 given that H0 is true. Probability of S bigger than 37 given that S is Poisson of 9 times 3. So you choose your way to calculate this, and my answer is 0.0263 to 3 significant figures. B, power of the test. To find the power of the test, I need to find the probability of a type 2 error first. And it will be probability of accepting H0 given that H0 is false. So that would give me probability of S less equal than 37 given that S is Poisson of 9 times 4 this time, which would give us 0.608,714. Therefore, the power of the test is 1 minus probability of a type 2 error, which gives me 0.391 to 3 significant figures. The essential bit here, very important, same as in all those types of questions, is to decide, to understand very well how the test statistic is calculated and to decide what is the sampling distribution of the test statistic. And then decide how odd or rare is your observation, on this distribution. And you decide if it's rare or not based on the significance level of the test. On this page and the next 2 pages, you have some solved problems. You can pause every time and try the question by yourself and look at the solution there. This example, it's interesting because we start with a binomial distribution, but when the workout is done and the decisions are made, this binomial distribution is approximated with a continuous one, with a continuous distribution. Why is that important or useful? It is because in some calculators we do not have an inverse binomial. Therefore, to find the critical region and the critical value, it's much easier if it's on a normal distribution, because then we can use the inverse normal. So it's much easier to find it rather than on a binomial distribution if we don't have a inverse binomial button. So that's why these approximations are useful. And remember also the continuity correction when you approximate a discrete distribution by a continuous one. This question is very similar to one that I've done already. So you might take a pause and try it by yourself.